Have you ever wondered how scientists calculate the exact seconds of celestial sunrises and sunsets? The mathematical horizon equation accounts for atmospheric refraction, diurnal parallax, and the disk's angular radius. Special trigonometric formulas yield 2-hour angle values for the moments of appearance and concealment. It is these rigorous geometric calculations that allow for the flawless prediction of day and night.
You know, when you watch the sunset, it seems like the most natural, simple thing in the world. But have you ever stopped to think about what's really going on behind that beautiful daily event? It's this incredible dance of geometry, physics, and our own perspective. So today, we're going to pull back the curtain on that spectacle and really dig into the science of how we calculate that exact moment of sunrise and sunset.
So, here's how we're going to approach this. We're going to start with a perfect, clean, simplified model of a sunrise. Then we'll start layering in the fascinating, messy complexities of the real world. Things like our atmosphere. And from there, we'll assemble a really powerful master equation that can predict the rise and set times for pretty much any object you can see in the sky.
All right, to really get a handle on this, we've got to start by stripping away all the complicated details. Let's just imagine a perfect, theoretical version of our world for a moment, a kind of clean slate so we can build our understanding from the ground up. Okay, so picture this. You're standing on a perfectly smooth, spherical Earth. There's no atmosphere at all to bend light or get in the way. From this purely geometric point of view, what is a sunrise? What's the definition? Well, in this perfect little world, sunrise is simply the instant that the dead center of the sun crosses that geometric horizon. And what's great about this is that it makes the math incredibly clean. It lets us calculate something called the hour angle, which you can just think of it as the object's east-west position in the sky. It's an angle that we can then very easily convert into a time. And this is the elegant formula for our perfect world. It's beautiful, right? It connects the hour angle t directly to your latitude on Earth and the sun's position up on the celestial sphere. But here's the kicker, the crucial catch. This whole thing hinges on the idea that the sun is at a zenith distance of exactly 90 degrees. And as we're about to see, in the real world, that's just not what happens.
Okay, so now it's time to bring our model back down to Earth. Literally. Our planet isn't some simple, airless ball. And those real-world factors, well, they dramatically change what we actually see. So we need to introduce 3 absolutely critical corrections.
The first one, and maybe the most counterintuitive, is our own atmosphere. It acts like a giant planet-sized lens. As light from the sun comes slicing into the atmosphere, it gets bent downwards. This effect, this refraction, is at its absolute strongest right at the horizon. And what that means is that the sun appears higher in the sky than it actually is. So get this, when you see the bottom edge of the sun just kissing the horizon at sunrise, its entire disk is still, geometrically speaking, completely below it.
Next up, we have parallax. You see, astronomers do their big calculations from the center of the Earth, but we're out here on the surface. That difference in our vantage point creates a small but very significant angular shift. Now, for incredibly distant stars, it's pretty much negligible. But for a close neighbor like our moon, it's a huge factor. We're talking a correction of nearly a full degree.
And our last correction comes down to what we even mean when we say sunrise. We don't say sunrise is when the sun's center hits the horizon. No, we define it as the moment we see that very first sliver of its top edge, what astronomers call the upper limb. So that means at the very instant you perceive sunrise, the sun's center is still below the horizon by an amount equal to its own radius. Okay, so we have our 3 key adjustments, right? The atmospheric lens effect, the parallax shift from our viewpoint, and the physical size of the object. Now we're going to combine them all to build our master equation, the one for the true zenith distance at the moment we actually see a sunrise.
So here's how we put the pieces together. We start with our ideal 90 degrees. We add the 35 arc minutes of refraction because remember, that makes the sun appear higher. We subtract the parallax, which also affects its apparent position. And finally, we add the object's radius to account for its top edge showing up first. And this gives us the actual angle from the zenith at the moment we truly see a sunrise.
So now we take that physically correct zenith distance and we plug it right back into our fundamental trigonometry equation. And what we get is this. This is our powerful, all-encompassing formula. This is the master key. It lets us accurately calculate the hour angle for the rise or set of any celestial body while accounting for all those major physical effects. And what's so remarkable about this equation is just how versatile it is. It's a universal tool. All we need to do is plug in the specific values for parallax and radius for whatever object we're looking at, and we can get a tailored, incredibly precise calculation. And this table just brilliantly summarizes how different those calculations can be. For distant stars, which are basically points of light, only atmospheric refraction really matters. For our sun, we have to add its radius into the mix. But look at the moon. For the moon, all three effects are critical, and its enormous parallax completely flips the script. The true zenith distance at moonrise is actually less than 90 degrees. So when we're calculating for the sun, we use a true zenith distance of 90 degrees and 51 arc minutes. That value neatly wraps up the 35 arc minutes from refraction and the 16 arc minutes from the sun's radius. Its parallax, of course, is negligible because it's just so incredibly far away. The moon, though. The moon is a completely different animal. It's so close to Earth that its parallax, 57 arc minutes, is the dominant factor, and it overwhelms the others. When you actually run the numbers, you find something truly mind-bending. At the moment of apparent moonrise, the moon's center is already, geometrically speaking, above the true horizon. All right, so we've done the heavy lifting. We've calculated the hour angle. But an angle isn't a time on your watch, is it? So for our final step, we need to convert that angle into a precise moment on the clock and also figure out exactly where on the horizon that event is going to happen. Now, because of how the cosine function works, our equation actually spits out two solutions for the hour angle, a negative value and a positive one. And it's wonderfully simple. The negative hour angle corresponds to the object rising in the east, and the positive hour angle corresponds to its setting over in the west. For the sun specifically, there's one last elegant little tweak. To get the time you'd actually see on your clock, we apply a correction called the equation of time. This factor, this eta, it accounts for the fact that the Earth's orbit isn't a perfect circle and our axis is tilted. It's really the final step that syncs up the motion of the actual sun with our nice, steady, uniform clocks. But before we even start any of this math, there's a much more fundamental question we have to ask. From your specific spot on Earth, will this celestial object you're looking for even rise and set at all? It all comes down to this fundamental mathematical constraint. For our hour angle equation to even give us a real answer, this inequality has to be true. If the numbers don't satisfy this condition, it's not a math error. It means that from your location, a rise or a set for that particular object is physically impossible. And this one mathematical rule perfectly explains two very cool astronomical phenomena. If an object's declination is too high for your latitude and you're in the same hemisphere, it becomes circumpolar. It just circles the celestial pole day and night, but never ever dips below your horizon. And on the flip side, if it's too far in the opposite celestial hemisphere, it will remain forever hidden from your view. So the next time you watch a sunrise, I want you to remember what you're really seeing. It's not just a simple daily event. It's the observable result of this profound conversation between gravity and optics and geometry. And it really makes you wonder, doesn't it? What other cosmic truths are hiding out there, right in front of us, just waiting for us to look a little bit closer?
Thank you, friends. Strive for understanding and become wiser. See you soon.